So thank you, Pierre, and the committee for inviting me. As you correctly said, I used to work for a CO2 storage operator. I've worked on many CO2 storage projects, including the early phases of Northern Lights, and I've left and I'm now working entirely in research. I'm now in the group called the Center for Geophysical Forecasting, and I'll show you about the work we're doing. And I'm also going to bring in examples from the SMILE EU project and the SHARP storage project. Um, so what I'm going to address, and I've only got 15 minutes, right? I could say a lot, but I'll try and keep to 50 minutes. What's the problem I want to discuss today? Um, this is a subsurface dog, okay? So we know how to do subsurface, and the operators can point to a long and successful track record of monitoring CO2 stores. So technically, there shouldn't be a problem, in my opinion. But these technical achievements do not connect with the public concerns about safety. So there is a problem, okay? Which maybe links back to legal questions. So what I want to ask is how can we monitor in a way that builds confidence in CCS projects and assures these stakeholders with concerns about safety that it really is safe? Because I genuinely think it's an extremely safe thing to do, CO2 storage. It's probably the safest thing human beings could do at the moment. But that doesn't necessarily convince our publics, as we saw. Individual projects are finding it very hard to progress to permitting. This is a published summary of all the monitoring methods applied at 5 CO2 storage sites: Sleipner, Insala, Snøhvit in Norway, Insala onshore Algeria, and then Decatur onshore USA, and Quest onshore Canada. And I won't go through all the table, but in the top, you have things that everybody's going to do. So that, wellhead monitoring, downhole fluid sampling, 4D seismic in one way or another is going to be done everywhere. What's also happening in the fourth row is that time-lapse VSP, which is vertical seismic profiling, which is a cheap time-lapse, is becoming very popular for the onshore sites. Could we do it offshore? Then we've got things like microseismic. It's been done onshore, and I'll show you how we're trying to handle the microseismic question offshore. And also downhole gauges and fiber optic technologies evolving and being adopted within the newer projects. Because Sleipner started in 1996, it had no downhole gauges. Very basic technology, one well, and it's relied entirely on time-lapse seismic, or nearly entirely on time-lapse seismic. But the technologies are moving. Now in Norway, every injector well must have at least 2 downhole gauges. Okay, so the technology is going to improve, and we're also working on, well, fiber optics do quite a lot of this job. So I will come on to that. So what I'm going to sort of suggest is there's 2 questions the public wants us to address. The could it leak scenarios. And I would want to show how the latest in 4D seismic detection could help us, along with knowledge of flow physics, to bring assurance about the could it leak question. And then there's the could it break scenario, which is understanding geomechanics. How does changes in rock pressure affect whether or not this storm will leak? And I'm going to try and dispel the notion that you inject CO2 and suddenly it cracks and leaks to the surface, unlike that sketch there. And part of that is going to be proactive seismicity monitoring. And for the cost and stakeholder assurance questions, I'm hoping, and this is more like a wish, that next generation monitoring solutions, which will be very high tech, a lot of fiber optic, will really do that job of assuring on a regular way. You say, look, this site is well monitored. You can see the data. That's the wish. So a little bit on flow physics. So CO2 is stored in the subsurface by a capillary interface at the boundary between the seal and the conductive unit, the aquifer or the reservoir zone. And this is what stops CO2 leaking. Whereas there is a feeling in the public that somehow it'll eventually just leak out. Well, no, it can't eventually just leak out. It's stuck there. The giant Troll gas field, which is next door to the Northern Lights project, has a 230-meter column of gas. It stayed there for millions and millions of years. 20 million years ago, there was a major tectonic event, and some of that oil did escape, and then there was a tilting event, and you can see the tilting in the oil column of the Troll gas field. Okay, so giant gas stores, they do have some leakage, but basically they've survived millions of years. And we can use that as an analog, as Northern Lights have done, to sort of help us inform on the CO2 storage thing. But I'm also keen to point out that a CO2 store is very different from a gas field. The CO2 is much less buoyant, and we have a much lower column height. So on the left-hand side, you see the Sleipner time-lapse seismic, where the maximum possible CO2 thickness at the top layer is about 20 meters thick. Okay, and you can easily calculate the buoyancy force in there. Oops, that wasn't what I meant to do. And that buoyancy force is only about 1.3 atmospheres of upwards force. It's very little, and it's held by that sealing layer, and it really can't escape, or it's very, very difficult for it to escape. How much is that force? Well, if you want a simple analogy, it's about 10 hot air balloons of upward pressure pushing on that thin seal. It's not a lot, okay? And I've tried to illustrate that in this YouTube video, which I like to promote, which is public communication of science, a bubble held behind a food sieve. Okay, you can look at that later. So getting on to the real projects, Anakari Furu has sort of compiled this nice data set, which I borrowed and stole. She's now published it. Just showing you how much was the detection, what was the degree of detection for time-lapse seismic for different sites. And if you just look at the top left of the diagram, the shallow sites, Ketsin, Sleipner, Tomakomai, they're all detecting of the order of 20 to 50 kilotons of CO2. So that's a realistic amount of detection. And if you look down at the bottom, Aquastor, using time-lapse VSP, the latest technology, down at 3 kilometers depth, they could also detect about 36 kilotons of CO2. So I think we're really going to have good detection, but there'll always be a certain amount that is not detected. So then, how do we address the question of what about the parts of the plume that you cannot detect? What if that bit of CO2 that you didn't monitor with seismic suddenly leaked to the surface? And you can see this in Snøhvit. On the right-hand side, you see the time-lapse seismic response. And in the left-hand side, you see a reservoir forecast of what the CO2 is actually doing in detail. And the technology is now that you can iterate between time-lapse seismic and reservoir simulation to try and optimize this problem. But again, what about that part you can't detect? Well, it's not like it's just going to go anywhere. It's flow physics that will constrain that. And we know the flow physics very well, and there's lots of experts in the room, like Roma, that understand the flow physics very well. So this leads to me my first little project. We've proposed a method called invasion percolation Markov chain. This is to keep the scientists happy. It's a sort of formalism of probability theory and physics. Invasion percolation is is when something percolates from one unit to another. And we've combined invasion percolation theory with the Markov chain, which is a well-established statistical technique. And to illustrate how we're using it, here you see a 5-layer stack in some anonymous CO2 reservoir. And we've set up the problem is that if that blue CO2 in layer 1 has a certain probability of breaching the seal at T1, then it will migrate to the next layer. And then there's another probability of migrating to the next layer, etc. And we set this up that there's an 8% probability of CO2 when it reaches the column height of breaching that seal. But then because the CO2 is left behind in the first layer by residual trapping and solubility trapping, not all of the CO2 can migrate to the next layer. So as a function of distance upwards through the system, the probability gets lower and lower and lower, so that by the time you've reached the 5th layer, it's, vanishingly small probability. Now, this is just a concept, but we would like to apply it in reality. And then another colleague called Geet Dutta just recently published in a geostatistics conference how we could apply this approach to looking at the value of information. So what we're saying is that, first of all, on the diagram on the left, you can say it's very, very unlikely the CO2 will migrate up 5 layers. But also, what's the layer you want to monitor? It's the first leakage layer, which is T2. And on the right-hand side, you see another stochastic model of when would you want to collect the seismic survey to detect if that leakage has happened at layer T2. And it turns out, in this case, to be after 12 years. And that's very valuable for you spending money on monitoring, because you then know when you need to monitor and what you need to monitor and how accurately you need to monitor it. And if you've shown that layer T2 is definitely not got CO2 below some detection threshold, you've really assured the whole system. That's the idea behind it. To sort of build technology into that, another smart PhD student, Ricardo Martinez, has been working on quantifying thin layers of CO2. And here he's using the seismic waves that propagate down through the layer and back up again, called diving waves, And we can use that analysis, and this is a Sleipner-based model, and the thin blue line is the known CO2 at layer 9. And we try and work out what's the thinnest CO2 layer we could detect. And without going into the paper, this has recently been published in JGI journal. We can get definitely detection down to 1, 2, or 3 meters of thickness, and we can quantify how much CO2 there is. And the idea is that you would then have a targeted seismic survey using both short offset reflection data and long offset reflection data to quantify how much CO2 is in that layer that you're worried about. So that's the first one. Could it leak? And then I'll be a little bit quicker on the rock mechanics one. Could it break? And this is a simple little sketch, which I won't spend time on. But the concept is that if you increase the pressure, so this is the famous Moore Coulomb failure diagram on the top right. If you increase the pressure in this formation, you will move the operating stress state closer to failure. But it's very important that you're not moving it to failure, you're just moving in the direction of failure. And we want to control that pressure to make sure that failure doesn't happen. And the key question usually is what we call critically aligned faults. So the red dotted line is a critical fault, which is most likely to fail in the vicinity of the injection store. And that's the thing you need to worry about. So how would you monitor critically aligned faults? In the Act Sharp project, we have a whole network with many, many case studies. I think it's 5 case studies with many partners looking at that problem, understanding stress and strain data and geomechanical data. So if you look at that simple column there, it's a sort of log scale of depth. We want to monitor the overburden, the caprock aquifer system, and the underburden, and understand the geomechanics. What would we do about that? Well, we basically need to think, what would we monitor? At the reservoir, we're going to use things like time-lapse seismic, but above and below the reservoir, we're going to use seismicity monitoring. And I've used up my 15 minutes. I'll take 3 minutes on the seismicity monitoring. So linking now to the Northern Lights project offshore Norway, for about 6 years, we've had this project, the HNet project, which has been trying to understand natural seismicity before we start injecting at the site. The picture here shows you our monitoring network, which we've been developing over the last years, combining onshore and offshore detectors. I'm going to hop over the technical slide, and I'm going to focus on the public communication slide. So we know the probability of earthquakes in this region. These are all natural earthquakes, not induced ones by any human activity. We know that events up to magnitude 3 or 4 occur in this region, and occasionally magnitude 5. And what we're working on is trying to improve the detection level to get us down to magnitude 1 or less, so that we can assure stakeholders that no induced or significant induced events are happening. And if you like, the key technology there is being able to show that your CO2 injection project is not associated with natural earthquakes, which are of magnitude 3, 4, or 5, which would cause concern. So we're mainly trying to avoid being accused of causing earthquakes, which are nothing to do with us. And to sort of improve on this technology for local detection, we've been using a seabed fiber, using sort of an analysis actually led by Total Energy with the other Northern Lights partners to listen to a telecoms fiber. And with that telecoms fiber, with no extra equipment installed, apart from an interrogator on the platform, we can detect 60 earthquakes in the vicinity of the Northern Lights project in 1 year of test. And we're now trying to move on to make this a permanent listening thing so that we're using a relatively low cost in-place fiber optic to detect earthquakes near to the CO2 injector without having to put in costly local detectors offshore. So that's how we're trying to address the question of public concerns about will it break? Okay. I'm going to hop over the costs, and this is all in the PDF online if you want to see it. And I will summarize and keep my chairman happy. So my contention is we can monitor in ways that build confidence about CCS and assure the stakeholders with their concerns. We don't want to avoid them. We want to address them. We do need to be proactive, and prevention is better than cure. Anticipation is better than going, whoops, something happened, like an earthquake near your site. So we're trying to help operators and also help the design with operators. What do you need to do early on in your project to assure stakeholders that there's nothing going to go wrong with this project? Thank you very much.